Hello बच्चों, this is the lecture number 16 of the unit Electrostatics, and in today's lecture we will cover 4 topics. First will be capacitor and capacitance, second parallel plate capacitor, third energy stored in a capacitor, and last capacitance of a parallel plate capacitor with a conducting slab and that with a dielectric slab. First topic is capacitor and capacitance. In this topic, firstly we will understand the concept of capacitor, that is, what is capacitor. It is a device which can store electric charge and hence electric energy when connected to a voltage source. It is made up of two closed conductors that are separated by a dielectric material. The plates accumulate electric charge when connected to a power source. On the basis of the shape of the conductor used, it is basically of three types. First is parallel plate capacitor. In this, conductors are of the shape of plates, and second is spherical capacitor. In spherical capacitor, the conductors are of spherical in shape, and third is cylindrical capacitor. In this, the conductor used are of cylindrical in shape. Second is capacitance. Capacitance or capacity of a capacitor is its ability to store charge. That is, how much charge a capacitor is storing, how much able it is to store charge is called its capacitance. A large capacitance means that more charge can be stored. It is denoted by capital C and it is measured in farads. The symbol of farad is capital F, but 1 farad is very large, so prefixes are used to show smaller values like microfarad, nanofarad, picofarad, etc. When a conductor is given some charge, its electrical potential increases. If a charge Q is given to the conductor, raises its potential by V, then it is found that Q is directly proportional to V, or we can write after removal of proportionality sign, Q is equal to CV. Here C is the proportionality constant and is known as electrical capacitance of the conductor. From the above equation we can rewrite C is equal to Q by V. Therefore, we may define the capacitance or capacity of a capacitor as it is the ratio of charge given to the conductor to the raise in its potential. There are some factors affecting the capacitance. First is capacitance depends on the shape and size of the conductor, and it also depends on the nature of the medium in which conductor is located. It doesn't depend on charge given to the conductor or raise in its potential or nature of the material of the conductor. The symbol of the capacitance is given here. First symbol is showing the fixed capacitor. In this capacitor, the capacity of the capacitor remains fixed. That is, it has a fixed value and we cannot change it. Next symbol is of polarized capacitor, also known as electrolytic capacitor. These capacitors are generally used when very large capacitance values are required. In this, instead of using a very thin metallic film layer for one of the electrodes, a semi-liquid electrolytic solution in the form of a jelly or paste is used, which serves as the second electrode, usually the cathode. The majority of electrolytic types of capacitors are polarized. Therefore, these are known as polarized capacitor, and the terminals of the capacitor must be connected according to its polarity. That is, it should be connected by its correct polarity. That is, positive to the positive terminal and negative to the negative terminal. Because incorrect connection will break down the insulating oxide layer and permanent damage occur. And third symbol is for variable capacitor. It is just opposite to the fixed capacitor. In variable capacitor, we can change the capacity of the capacitor. So it is called variable capacitor. Here we are going to discuss the differences between capacitor and battery. First is, in capacitor, potential energy is stored in the form of an electric field, and in battery, the potential energy is stored in the form of chemical energy, which is later converted to electrical energy. Second, the function of capacitor is it draws energy from the circuit, stores and then release the energy. The function of battery is to provide energy to the circuit. Capacitor is a passive component of a circuit. Here passive components means the components that don't need an external power source to function. Battery is an active component of the circuit, and just opposite to the passive component, active components are those that needs an external power source to control or modify electrical signals. Capacitor is generally used for AC applications. It blocks the DC component of the circuit, but battery is used as the DC components. Next is, charging and discharging rates are faster than a battery in capacitor because it stores energy directly to the plates. But in battery, charging and discharging rates comparatively slower because of the conversion of chemical energy to electrical energy. Next is, in capacitor, voltage gets rapidly decreased, but in battery, the battery provides a relatively constant voltage when discharging. Next, capacitor discharges instantaneously. That is, it takes very less time for discharge, approximately tends to 0. And in battery, it runs for a longer time. The life cycle of capacitor is 1 million or 30,000 hours, and that for battery is 500 or more hours. Capacitor cost is higher, but battery is cheaper as compared to capacitor. Last is, the polarity of capacitor must be same at the time of charging and using, but in battery the polarity is reversed at the time of charging and using. Next point is principle of capacitor. Now we are going to understand what is the principle of the capacitor and how we can construct a capacitor. As we know that a capacitor is an arrangement for storing large amount of electric charge and hence electric energy in a small space. We will understand its principle under these points. First is, let us consider an insulated metal plate A and let some positive charge be given to this plate till its potential becomes maximum. Now consider another insulated plate of metal B held near plate A at desirable distance. By induction, a negative charge is produced on the nearer face of B and an equal positive charge develops on the farther face of B, as shown in figure A. The induced negative charge tends to decrease the potential of A, and induced positive charge tends to increase the potential of plate A. As the induced negative charges of plate B is closer to plate A, the effect of these charges will be more and hence the overall potential of plate A will get reduced. Now some more charge can be given to plate A to increase its potential to some maximum value again. Thus, in this way, the capacity of A gets increased by bringing another uncharged capacitor in its vicinity. Now connect B to earth. The induced positive charge on B being free flows to earth because the negative charges are bound to the positive charges of plate A, so they will not flow to the earth. Due to induced negative charge on B, potential of plate A greatly reduced. Thus, a large amount of charge can be given to plate A to raise its potential to maximum value. So, we can say by bringing an insulated uncharged metal plate near an insulated charged metal plate at some desired distance, we can increase the capacity of the conductor by making such a device on this principle. Or, in other words, we can say capacitance of an insulated charged conductor is increased considerably by bringing near it an uncharged earthen conductor. Next point is capacity of an isolated spherical conductor. For this, let us consider a spherical conductor of radius r and center at O. Let plus q charge distributed uniformly on its outer surface, and as we have studied in previous lecture, the charges distributed on the surface of the conductor can be assumed as concentrated at its center, as shown in figure. So, we can write the potential at any point on the surface if the system is in free space. V is equal to Q by 4 pi epsilon naught into R. As we know that capacitance C can be written as Q by V. Therefore, by putting the value of V here, we get C is equal to 4 pi epsilon naught R. This is the capacitance of an isolated spherical conductor. From this equation we can see capacity is directly proportional to the radius of the spherical conductor. Therefore, we can say larger the radius of the sphere, greater will be its capacitance. Next topic is parallel plate capacitor. In this, we will study the construction of parallel plate capacitor and then derive the formula of its capacity. And finally, we will discuss the dependence of capacity on different factors. So firstly, its construction. It consists of two thin conducting plates of area A held parallel to each other at a suitable distance d. The plates separated by an insulating material like air, mica, glass, etc. One plate is insulated and other is connected to earth. As we have studied in the principle of capacitor, plus Q amount of charge is given to one plate, which is shown in figure on left side, and due to induction the minus Q charge will induced on the second plate, and rest of the points I am not going to discuss here, as you all know very well. So let's move on. Surface charge density is given by sigma is equal to Q by A, and the electric field intensity in between the plates is given by E is equal to sigma by epsilon naught, which we have studied in first chapter. So by putting the value of sigma, we can get E is equal to Q by epsilon naught into A. Here we are considering that electric field localized between the plates as uniform throughout. That is, electric field is uniform throughout the space in between the plates. So the potential difference between the two plates can be written as V is equal to E into D by the formula which you have studied, which was potential gradient, that is E is equal to dV by dr. By putting the value of E, we get V is equal to Q by epsilon naught A into D. Now we know that the capacity of a parallel plate capacitor is given by C is equal to Q by V, and by putting the value of V here, we get the capacity of a parallel plate capacitor C is equal to epsilon naught A by D. Here capacity of a parallel plate capacitor depends on area of the plate, distance between the two plates, that is separation of the two plates, and the medium involved in between the plates. As we have studied in previous slide, that capacity depends on the shape and size of the conductors, which is area and the separation between them. And second, it depends on the medium in which conductor is located. And here the medium we have taken is air or vacuum. So epsilon naught is denoting the medium here in the formula. Next topic is energy stored in a capacitor. As we know that capacitor is an arrangement for storing large amount of charge and hence electrical energy in a small space. So here we are going to find out the amount of energy that a capacitor can store. As we know that work has to be done to transfer charges onto a conductor against the force of repulsion from the already existing charges on it. This work is stored as a potential energy of the electric field of the conductor. All these things we have studied in the topic potential at the starting of this chapter. Now, suppose a conductor of capacity C is at a potential V and let Q be the charge on the conductor at this instant. The potential of the conductor when the charge on it is small q, which is less than the total amount of charge can be given to the conductor, is given by V dash is equal to Q by C. Here in this case, the capacitor is not fully charged. It has acquired some charge small q, which is less than the total charge which it can acquire. Now, since the capacitor has acquired small q amount of charge, so if we are transferring some more charge equal to dq, which is very small value of charge, the work is to be done. So we can write the value of very small work done dW in giving an additional charge dQ to the capacitor. dW is equal to V dash into dQ. By putting the value of V dash, we get dW is equal to Q by C into dQ. Now to find out the total work done in giving net amount of charge capital Q to the capacitor, we will have to integrate dW from the charge limits 0 to capital Q, that is when conductor or capacitor has charge 0 initially at time t is equal to 0, and when it acquires the total amount of charge, which is capital Q. So net work done W is equal to integral 0 to Q by C into dQ. Here 1 by C will be out of integration because it is a constant value. So integration of Q will occur, and by integrating Q from the limits 0 to capital Q, we get the total work done W is equal to 1 by C into Q square by 2. Since the electrostatic force is conservative, this work is stored in the form of potential energy U of the capacitor. So we can write U is equal to W, and which is again equal to 1 by C Q square by 2, or half Q square by C. Here we can rearrange the equation by putting the value Q is equal to CV. The energy stored can also be written in the form of capacitance and raise in potential V, U is equal to half CV square. And again, by putting CV is equal to Q, we can rewrite the energy stored in the form of total charge given to the capacitor and raise in its potential, which is U is equal to half Q into V. Here is an additional topic, which is energy density of a parallel plate capacitor. So, energy density of a parallel plate capacitor is the total energy stored per unit volume of the capacitor. Therefore, we can write energy density is equal to energy stored per unit volume, that is U by V. By putting the values of U and V, here V is the volume of the capacitor, not potential, and from the figure we can say that the volume will be area of the plate into separation between the two plates. By putting the value of C is equal to epsilon naught A by D and V is equal to E into D, we get the energy density U is equal to half epsilon naught into E square. This expression will be used later in the chapter electromagnetic wave. So remember this expression. Last topic is capacitance of a parallel plate capacitor with a conducting slab and that with a dielectric slab. In this topic, we will derive the expression for capacitance of a parallel plate capacitor in two different cases. First will be when a conducting slab is inserted in between the two plates of the capacitor, and second will be when a dielectric slab is inserted in between the two plates of the capacitor. For this, let us consider a parallel plate capacitor having charge of magnitude Q on each plate as shown in figure. Suppose the separation between the plates is D and the system is situated in air or vacuum. Now the capacitance of a capacitor is given by C naught is equal to epsilon naught A by D. So first case, when a conducting slab is inserted in between the plates of a capacitor. When a conducting slab of area A and thickness T is less than D, that is separation between the two plates, is introduced between the plates of the capacitor, the free charges in the conductor will flow and plus minus Q charge appear on the two faces of the conducting slab as shown in figure. As we know that the electric field inside the conductor remains 0, so the potential difference between the plates is given by V is equal to E naught into D minus T. As we can see in the figure, E is equal to 0 in thickness T and the electric field is only in rest of the space except the conducting slab. Therefore, the total electric field is in the space D minus T. So by the expression of potential gradient E is equal to dV by dr, we have written this expression. Now putting the value of E naught, which is sigma by epsilon naught, we get V is equal to sigma by epsilon naught D minus T. In the last expression, we can put the value of sigma, which is Q by A. So we get potential V is equal to Q by epsilon naught A into D minus T. As we know that capacity of a capacitor is given by C is equal to Q by V. Therefore, by putting the value of V, we get the final expression after solving. C is equal to C naught upon 1 minus T by D. Here we can see that C is greater than C naught. Therefore, by inserting a conducting slab in between the two plates of the capacitor, the capacity of the capacitor will get increase. Second case is, and a dielectric slab is inserted in between the plates of a capacitor. When a dielectric slab of area A and thickness T, which is less than the separation between the two plates, is introduced between the plates of the capacitor, polarization in the molecules of the slab occur, and because of this polarization, an electric field EI is induced within the dielectric opposite to the direction of E naught, and the effective electric field in dielectric slab becomes E is equal to E naught minus EI, as shown in figure. Now we can write the potential difference between the plates. V is equal to E naught into D minus T plus E into T. As we can see in the figure, E naught electric field is in the space D minus T, and E is the electric field in the space T. Now we know that the dielectric constant is the ratio of E naught to the E, or we can write E is equal to E naught by K. By putting the value of E in this equation of potential, we get V is equal to E naught into D minus T plus E naught by K into T. E has been taken common from the expression, so V is equal to E naught D minus T plus T by K. Also we know that E naught is equal to sigma by epsilon naught, which is Q by epsilon naught into A. So by putting the value of E naught in the expression, we get V is equal to Q by epsilon naught A into D minus T plus T by K. Now the capacitance of the capacitor is given by C is equal to Q by V. By putting the value of V from the above expression, we get the final value of capacitance. C is equal to epsilon naught A by D minus T into 1 plus 1 by K. We can further solve this expression. So we get C is equal to C naught upon 1 minus T by D plus T by D into K. From this expression again we get C is greater than C naught. Therefore, by introducing in dielectric slab in between the plates, its capacitance increases. Homework: define 1 farad and find out the dimensions of capacitance. Next is find out the ratio of capacitance of a capacitor with dielectric in between the plates to that of the same capacitor with air or vacuum in between the plates. Third is derive an expression for equivalent capacitance for combination of capacitors in series and in parallel. 4. Find out the total energy stored in a combination of capacitors. And last is study common potential and loss in energy on sharing charges. Thank you.